Okay, this is the first part of lecture 4, and it's the history of the atomic theory, this portion. And the slide lecture PowerPoint is, as you can see, oh, no, hang on, forgot to share. There we go. You can see at the top, it's lecture atomic theory, that's the slides. So we have a current view of the atom, but how did we get there? It's happened in steps. A lot of steps. We take it for granted that the atom has a nucleus with protons and neutrons, and it has electrons around it in spheres or in specific regions, but we didn't always realize that. So I'm going to go over how we got from here from there. The idea of what are the smallest particles that things are made of actually was being considered 500 BC. So about, 2,500 years ago, 2,500 years ago. They were called natural philosophers back then, scientists were. It was actually a combination. Science and religion were one unit. So philosophy was big. This was Aristotle and Plato and Socrates, and looking at the world around us to say, what is all this? And what does it mean? From there, the idea of the atom came from. And since then, through all the different processes, which we'll go over in this lecture, we've gotten the mass laws. And these are very critical to how we are able to look at our observations and use them to make chemical conclusions about the chemistry that's happened. So in 1787, which kind of kicked off the re-emergence of scientific thinking, because we were in a true dark ages. Scientific thinking was actually illegal. To get you put in jail. Galileo was put in jail for thinking scientifically. Lavoisier came up with the law of conservation of mass, which I brought up in the previous lecture, that matter is neither created nor destroyed. And we now know that that actually includes energy. Energy is neither created nor destroyed. As you saw in the previous lecture, it is exchanged between your system, which is your reaction, and your surroundings. So if your reaction needs energy, it takes it from the surroundings. That might be the test tube wall. It might be the air right around the experiment. If it gives off energy, it has some left over, it's released into the surroundings. And that's why we talk about the temperature in the surroundings will increase. It came from the excess energy of the reaction. So matter and energy are neither created nor destroyed. 1804, we have Proust, the level of definite composition, because during this time, an atom was just a ball. There was no distinguishing characteristics. They thought the atom was the smallest particle. No neutrons, no protons, no electrons. So Proust came up with the law that all samples of the same compound, so if I have a pile of sodium bicarbonate over here, or sodium sulfate in this image, and a pile over here, and I take a sample of each compound will have the same proportions by mass of the elements. Each of the proportions will be identical, and that was really important. And the law of multiple proportions, Dalton in 1808, was that when you're combining two elements, so you're making a molecule, you have a chemical connection between two atoms, they have to combine in whole number ratios. This was actually a new concept. But this absolute factor of it enabled the research observations and conclusions to be applied. Okay, I have one part of this and I have one part of this gas and one part of this gas were used to make this new gas. By this law, I know that it was one atom, each molecule is one atom of oxygen, one atom of carbon, or 2 and 2, but it's whole numbers. So let's go back to 400, 450 BC. Democritus came up with the first atom. An atom is from atomos, from Greek. It means cannot be broken. Atomos, indivisible. The smallest part. Before Democritus came up with his atom, and his atom was just a sphere. It truly was the tiniest particle. People thought that one of the theories was that a substance could be broken down to smaller particles, but of the same substance. And the particles would have the characteristics of that substance. So a tree could be broken down into teeny tiny little tree parts, but they would still have characteristics of a tree. Cheese could be broken down into little bitty cheese parts. The smallest particle was still cheesy. It still had the properties of cheese. Well, Democritus said, no, it actually can be broken down into a simpler building block, and it's just a sphere, and it's called an atom, cannot be broken apart. Now, this wasn't popular. Oftentimes, scientific theories that we now know are true or accepted as fact, when they first came around, they were not accepted. When the planetary system of the Earth and the planets going around the sun came around, it was right around this time period, and it was laughed off. And it would emerge every so often, every 500 years or a few hundred years, and it would not be accepted. It took a long time for the theory that the Earth revolves around the sun to be accepted, because back then it was considered that everything revolved around the Earth. Everything revolved around us. So Democritus' theory that the atom was the smallest particle, the sphere, was just laughed off. Aristotle had a different theory which was much more accepted, that, and let me enlarge this, that all matter was made up of 4 elements. So you had the one theory that the tiniest particle was a tiny piece of the whole. Aristotle's was 4 elements: earth, air, fire, and water. And so if something, the way we perceived it had to do with the component of earth or air or fire or water that made it up. If something was hot, or I don't know. It's actually interesting if you look that up. So that was actually the more accepted view. And then we had another view which said it was made up of the 4 humors. So it took a while for Democritus to get his theory to be accepted. Eventually it was. So over the years, this is simply timeline. The ones in the dark circles are the ones you want to know. But this is just a flow of some of the important dates. And as you can see, really nothing happened until 1787. And then early 1800s, there was a little bit. John Dalton's postulates were very important, were critical. Then there's a little bit of a lag, and then late 1800s, it really picked up. Because once discoveries were made and accepted, it just kind of opened doors, because science builds on itself. Each discovery leads to a new discovery. It makes it faster. All right. So John Dalton, and he is right here, 1803 to 1808. So that's 200 years ago. It's still all fairly new. All of these are understanding in chemistry. He put together a theory that explained these mass laws. Now, still, the atom was still just a round ball. So his postulates were that all matter is composed of atoms, indivisible and destructible. Okay, that's what Democritus says. All atoms of a given element are identical. All hydrogen atoms are going to be identical in mass and chemical properties. All aluminum atoms will be identical in mass and chemical properties. So if it's the same element, it's going to be the same. No matter how much of it you have, the chemical properties are not going to change. But atoms of different elements are different. This was critical so that if you did experiments and you got results, you could attribute the results to what you use in your test. Atoms are not created or destroyed. They are rearranged. Again, a lot of these early experiments were done with gases in closed containers. So by knowing that that gas didn't go anywhere, if you knew what you started with, I started with hydrogen, I started with oxygen, I end up with water vapor, then you know that water vapor was made up of a combination of hydrogen and oxygen atoms, because that's what you used. It couldn't have gone anywhere. They were not created or destroyed or rearranged. So they figured out the ratios of each of these by mass and by volume. And atoms combine in simple fixed whole number ratios. We have no fractions in chemical molecules. So early 1800s, and we still use those today. So here's a little bit of a timeline, give you a sense of how long that took. So 1897, almost 100 years later, now we now have electricity. So electricity can be used to for research. And J.J. Thomson would play around with the cathode ray. Sometimes you'll see his name with a P, sometimes you will see it without. It's kind of like one's an American spelling and one's a British spelling. You can actually find video on YouTube, excuse me, of him talking, which is really cool. He gives a little 6-minute lecture about the discovery of the electron and its use in like 1930. So he came up with the discovery of the electron using cathode ray tubes. Before this, it was just a sphere. All right, he knew that your atom, your unit, had a net neutral charge. So he knew when he discovered these negative charges that they had to be embedded in a positive charged matrix, because the net unit had a no charge, which means they had to be balanced. So he knew if there was a negative, there had to be positive. And he considered that was the matrix, the stuff. You know, this is called the plum pudding model. As I explained, the plum pudding is a British dessert filled with dried fruit and nuts, which maybe you can think of it as the blueberry muffin model. And the electrons are the blueberries scattered all in there, and the muffin is the positive matrix. A cathode ray is a stream of electrons, but they thought it was just a stream of light originally. It was particles, and that shouldn't have behaved like. But what he did is he did the cathode ray, plugged it in, got a cathode ray, and when it hit the end piece, it would light up because of the coating. And then he put charged plates, positive and negative, on either side. When he did that, his cathode ray, if he used a cathode ray, bent. Well, he knew it could only be bending because of the charge that he applied on the plate, and it bent according to the charge. So he did another discovery using magnets, because if you apply a magnet to a negative charge, it will bend away. And this is an example of what the cathode ray looks like, of the experiment that he did.
This is a cathode ray tube. Inside, there's nothing inside. It's actually a vacuum tube. So there's nothing but a vacuum on the inside. And it's called a cathode ray tube because this is the anode and this is the cathode. When it's hooked up to an electric current, like I'm about to do here, you can see a beam moving across. You might think it's light, but when you take a magnet to light, it does it do this. You can see that it's bending or deflecting away from the magnet, so we know that it's not actually light. What J.J. Thomson summarized was that he was seeing a piece of an atom flying from one end of the cathode ray tube to the other, and that the piece of the atom that he was seeing was negative based on the end of the magnet that was causing a repulsion. So the negative end of the magnet was causing repulsion, therefore the particles must be negative.
Okay, and since he knew, at that time it was considered that the atom was the smallest particle. However, he knew that an atom is neutral, it's not charged, but something was charged. He knew it had to be part of the atom. He called them corpuscles. They were not called electrons originally. They were called corpuscles, like blood corpuscles. So that was the first discovery of something smaller than an atom. And he thought it was just embedded in a positive matrix. So that was the next version of an atom. And you do want to know these models. So there's 1897. And then Rutherford, while trying to support doing experiments for whatever reason that would support that model, he actually found the results of his experiment did not support his hypothesis, actually behaved in a way that did not fit with his hypothesis. And he realized there was something going on here. So he took alpha particles. Alpha particles are large, positively charged particles. And he shot them through gold foil. And there was a collar around here that would, when the alpha particles went through and hit, they would light up. Just a little flash. So his theory was that because the alpha particles were so large and your charged matter was so small, there would be no effect. It's like, you know, throwing a football or a baseball through something very, very tiny. It would just go right through. That was what he thought would happen. But that's not what happened. The alpha particles, when they went through, they deflected some of them. Most of them went straight through. But some of them deflected strongly, and some of them actually went straight back. And he was like, wow. In the book, it gives some of his quotes. He was really excited about this. And on looking at it, analyzing, thinking about it, he came up with the conclusion that in order for this deflection to occur, especially the one that went straight back, there was a strong enough positive charge in the atom that was big enough to actually bounce that back, because these alpha particles are pretty soluble. So these are positive charges, and he realized that they were hitting another solid positive charge big enough to make it bounce back. So he took these positive charges that were originally considered to be just in part of the matrix and put them all in a centralized nucleus. And a nucleus is generally the word used for the center of something. And so that is how we got our protons in the center. And because most of the particles did go straight through, only a few bounced back, he theorized that the rest of the atom was mostly empty space. And so the electrons, because Thomson did give a size to the electron using mass to charge ratios, that the electrons, they're tiny and they were around this nucleus, and then it was mostly empty space. So now we have, with Rutherford's work, we have electrons around the nucleus. We have a nucleus that contains the protons. So now we have more structure. 1911, just over 100 years ago. That was not very long ago. Think about that. And here's an example of what he theorized. Okay, so here's Rutherford. So we're getting closer here. These are both great links. I highly recommend that you look at them. Crash Course, very entertaining. Gives a summary of this history. Tyler DeWitt is a bit more methodical and slower paced, but also excellent. So I highly recommend you check out both of those links. They're not that long. All right. So here's what we have so far. And I do want you to know these models. And you don't need to know the year it happened, but know kind of the timeline, roughly. So the original atom for 2,000 years was just, or 1,900 years or whatever, was just this tiny ball of nothing, just a ball. No definition. And then we have the plum pudding model, which puts separated negative and positive charges. But the negative charges have mass. They're actually particles. Rutherford said, oh wait, the positive is actually concentrated in the middle. and the rest is mostly space. So the electrons are just randomly around in the space. They're so tiny, they don't take up much room. But the protons are in a nucleus in the center. And then Bohr in 1913 came up with the planetary model where he said, okay, no, these electrons are not randomly in space. They are in specific orbits, specific regions, and they can only occupy that region. And they circle the nucleus just like our planets circle the sun. That's why it's called the planetary model. An electron can't be in this in-between space. It's only in the specific orbit, and they build outward. And then the current model we use is a quantum mechanical model, which you will learn in CHM1. So we're using Bohr's model as our model of how to place the electrons. It's a simpler version, but the concept is the same. So when you go to CHM1 and the more detailed model, that part you'll have a good understanding of. So this is also a good site. It gives just a nice little visual of the timeline. So I also recommend you check that out. Okay, so this is the history part, and I'll stop this one here. And then we'll go to the next video will be part 2, which is going to be talking about the specific aspects of an atom, ion, isotope, the electron, the neutron, the proton. So we'll get the details of these guys.